In 1957, a graphic artist in the Netherlands opened an envelope from a mathematician in Toronto, and inside was a picture of something that is not supposed to exist. It was the edge of an infinite world. He said the figure gave him quite a shock. He spent 3 years carving it into wood, and today the image hangs framed in living rooms all over the planet. Infinitely many angels and devils, complete, inside one circle. But here is what nobody tells you about that picture. It is not a fantasy. It is a mathematically exact map of an infinite universe, boundary included, drawn with the same technique physicists use to chart space-time itself. You have been told your whole life that an infinite universe can have no edge. Physics says otherwise. It can define one, draw one, and calculate standing on it. And the strangest result in modern science suggests that boundary may be more real than everything it contains, that the entire universe, including you, may be written on its surface. So what would the edge of an infinite universe actually look like? By the end of tonight, you will know exactly. Get cozy. Subscribe if you haven't yet, because by the end of this, the word edge will never mean the same thing again. Now, let's slowly slip into this. Part 1. The answer that was supposed to end the question. Every child eventually asks the question, and every adult eventually gives the same answer. The question is some version of this. If I traveled far enough, past the last star, past the last galaxy, past everything, what would I find? What is at the edge of the universe? And the answer, delivered with the confidence of settled science, is that the question itself is broken. There is no edge, we are told. Either the universe curves back on itself like the surface of the Earth, so that traveling far enough simply brings you home, or it goes on forever, in which case there is no far enough, no last thing, no wall, no window, no end. Either way, the conversation closes. The question is filed away with the other childhood questions we are taught to stop asking, and most of us stop asking it. Tonight, I want to reopen that file, because the standard answer, the one you have almost certainly been given at some point in your life, is wrong. Not wrong in the way a myth is wrong. Wrong in a subtle and much more interesting way. It is wrong in the way a door is wrong when someone tells you it is a wall. For a little more than 60 years, mathematical physics has quietly possessed the tools to define, to draw, and to calculate with the edge of an infinite universe. Not a metaphorical edge, not a poetic one, a boundary with a precise location on a map, with structure, with geography, with rules about who may arrive there and who may not. Physicists use this boundary every working day. The most famous calculation of the 20th century was performed by standing on it. And in its most radical form, this boundary may not merely mark where an infinite universe ends. It may contain the universe. It may be the place where everything that exists, including you, is written down. That is the claim we are going to spend tonight unpacking, slowly, piece by piece. And I want to be honest with you from the start. The question in our title, what would the edge of an infinite universe actually look like, is a question we will not answer until the very end. Not because I am hiding the answer for drama, but because the answer cannot mean anything until we have climbed the ladder that leads to it. Each rung looks impossible from the rung below. That is simply how this subject is built. Before the climb, it is worth remembering how old this question is, because you are in ancient company every time you ask it. 24 centuries ago, a Greek philosopher named Archytas posed what may be the first thought experiment about the edge of everything. Suppose, he said, that the universe has a boundary. Now walk to it. Stand at the supposed end of all things, raise your arm, and throw a spear outward. One of two things happens. Either the spear flies onward, in which case there was more space beyond, and this was never the edge at all, or the spear stops, in which case something stopped it, and that something is itself beyond the supposed edge. Either way, the edge retreats. Repeat the argument forever, and you seem forced to conclude that the universe can have no boundary. The Roman poet Lucretius repeated the spear argument about 3 centuries later, and it has never really left the human imagination since. Others took the opposite road. Aristotle built a cosmos that truly ended, with a final sphere carrying the fixed stars, and beyond that sphere, in his account, there was neither place, nor time, nor anything at all, not empty space, not darkness, nothing, in the strictest sense, a nothing so complete that even the question of what lies there was declared meaningless. In the 15th century, a cardinal named Nicholas of Cusa wrote that the universe could have no circumference and no center, or rather that its center was everywhere and its circumference nowhere, which is a sentence that would sit comfortably in a modern cosmology textbook. A century and a half later, Giordano Bruno insisted the universe was infinite, filled with countless suns and countless worlds, and that conviction was among the charges that led him to the stake in the year 1600. And when Immanuel Kant tried to settle the matter with pure reason in the 18th century, he concluded that reason could argue both sides with equal force, that the finitude or infinitude of the world was a question our minds could pose but never close. He called it an antinomy, and he placed it first on his list. Even Einstein flinched at this question. When he applied his brand new theory of general relativity to the whole universe in 1917, he deliberately built a cosmos that was finite and curved back on itself. And one of his reasons was that an infinite universe forces you to specify what happens infinitely far away. In the mathematics of physics, you cannot solve the equations for a system unless you say what the situation is at its boundary. For a universe with no boundary, at distances without end, what could such a specification even mean? Einstein found the prospect intolerable, so he chose a universe shaped like the 3-dimensional surface of a sphere, closed, tidy, edgeless, and he moved on. The discomfort he was avoiding has a name in the field. It is called the problem of boundary conditions at infinity, and I want you to hold on to it, because the entire story we are telling tonight is, in one sense, the story of how physics stopped avoiding that problem and learned instead to solve it. Here is what makes the modern chapter of this story so strange and so worth your evening. Physics did not settle the ancient argument by picking a side. It did something neither Archytas nor Aristotle nor Kant imagined was available. It found a way for both sides to be right at once. The universe can be infinite, with no wall in space for any spear to strike, and it can still have an edge, a boundary as definite as a coastline, provided you understand what kind of thing that edge is and where it lives. The edge of an infinite universe is not a place you travel to. It is something far stranger, and by the end of tonight, you will know exactly what. So this is our ladder for the night. We will start small and cozy, with the humble edges astronomers already measure, the horizons that fence in the visible universe, and we will see why none of them counts as a true end of anything. We will meet the 3 possible shapes an entire universe can have, and discover that our own sits unnervingly on the border between the finite and the infinite. We will watch physicists mistake a flaw in their own maps for a wall in reality, for 40 years, and then watch one man fold the whole of an infinite space-time onto a single sheet of paper without breaking a single angle. We will find that the edge he drew has an anatomy, with separate destinations for matter and for light. We will see the edge put to work, in the calculation that made a dying man the most famous physicist on Earth. And then the story will turn genuinely strange, through a woodcut hanging in living rooms all over the world, into a universe shaped like an endless saddle, whose infinitely distant boundary turns out to be answering back. The question of what that means, and what it would mean for you, is where we will end. For now, hold the child's question in your mind, the one you were told was broken. What is at the edge of everything? Keep it close tonight, because the first thing we have to do is something that sounds anticlimactic and is actually profound. We have to visit the edges we can already see and understand why every single one of them is a fence and not a wall. Part 2. The Picket Fence. The universe you can actually see has an end, and astronomers know exactly where it is. That sounds like it contradicts everything I just said, so let us take it slowly, because the nature of this particular end is the key that unlocks the whole night. Light travels fast, but not infinitely fast, and the universe has not existed forever. It has existed, by our best current measurement, for about 13.8 billion years. Put those two facts together, and something follows immediately. There has only been so much time for light to travel, which means light from sufficiently distant places has simply not had time to reach us yet. No matter how large or powerful your telescope, there is a distance beyond which you are not seeing anything, not because nothing is there, but because the mail has not arrived. The region we can see, the sphere of everything whose light has had time to get here, is called the observable universe, and its outer limit has a formal name. It is called the particle horizon. Now, you might guess that the particle horizon sits 13.8 billion light-years away, since the universe is 13.8 billion years old. The real number is stranger, and the reason is one of the most important ideas in cosmology. Space itself has been expanding the whole time that ancient light has been traveling. A galaxy whose light left it billions of years ago has been carried away from us by that expansion ever since, the way a walker on an airport moving walkway ends up much farther along than their own steps would carry them. When you account for the stretching, the matter whose light is just now arriving from the earliest times sits, today, about 46.5 billion light-years away. That makes the observable universe a sphere, roughly 93 billion light-years across. To give that number some texture, our entire galaxy, with its hundreds of billions of stars, is about 100,000 light-years wide. The observable universe is nearly 1,000,000 times wider than that, and it contains, by recent counts, somewhere in the neighborhood of 2 trillion galaxies. That is the size of the visible patch, not the universe. The patch. There is a second horizon, and it is crueler than the first. Since the late 1990s, we have known that the expansion of the universe is accelerating, pushed by something we call dark energy, whose nature remains one of the great open problems in physics. Acceleration changes the rules of the game. In a universe that expands faster and faster, there are galaxies whose light, leaving them tonight, will never reach us. Not in 1 trillion years, not ever. The distance that separates the reachable from the unreachable is called the cosmic event horizon, and it currently sits around 16 to 17 billion light-years away. Anything beyond it has, in a practical sense, already left our story. We may see its old light for a long while yet, the way you see the glow of a ship that has already sailed over the curve of the sea, but no new message from there will ever arrive, and nothing we send will ever get there. The particle horizon is the limit of the visible past. The cosmic event horizon is the limit of the visible future. The cruelty of the event horizon deserves one more moment, because the numbers are sobering. When astronomers run the accounting, they find that most of the galaxies in our observable universe, roughly 94% of them, by some estimates, have already crossed the line. Light leaving them today will chase us forever across an expanding gulf and forever lose ground, like a runner on a treadmill whose belt keeps speeding up. In the far future, this thins the sky itself. Given enough time, everything beyond our own gravitationally bound neighborhood, the Milky Way, Andromeda, and their small entourage of companion galaxies, will slip past the point of no return, and the merged galaxy our descendants might inhabit would look out on a darkness that carries no hint that other galaxies ever existed. The universe is not just bigger than our fence. It is quietly, continuously, moving beyond it. Between them sits a third boundary, subtler than either, called the Hubble sphere. It lies at about 14.4 billion light-years, and it marks the distance at which the expansion of space carries galaxies away from us at exactly the speed of light. Beyond it, galaxies recede faster than light. I want to pause on that, because it sounds like a violation of the most famous rule in physics, and it is not. Einstein's speed limit says that nothing may move through space faster than light. It says nothing about how fast space itself may stretch. The galaxies beyond the Hubble sphere are not speeding through the universe. They are sitting almost still in their own neighborhoods, while the distance between us and them grows, like two ants standing quietly on a rubber sheet that someone is pulling. No rule is broken, and remarkably, light from some of those faster-than-light regions can still, eventually, reach us, because the horizon itself shifts as the universe evolves. So there they are, three edges, each with a precise distance, each of which you could mark on a cosmic map. And now comes the observation that changes what all of them mean. Every one of those horizons is centered on us. Draw the observable universe, and we sit at the exact middle of the sphere. That is not because we occupy a special throne at the center of creation. It is because the horizon is defined by what light has had time to reach our eyes. An astronomer in a galaxy 10 billion light-years away has her own observable universe, a sphere of the same size, centered exactly on her. Part of her sphere includes regions we will never see, and part of ours includes regions she never will. Neither of us is at the center of the universe. Each of us is at the center of our own view. Here is the picture I want to leave in your mind, borrowed from the way working cosmologists themselves talk about it. Imagine an unbounded plain, stretching away in every direction, without end. Somewhere on that plain is a small plot of land, and around that plot, someone has built a little picket fence. From the point of view of the plain, the fence means nothing. It marks no change in the grass, no border in the soil, no edge of anything real. But from inside the fence, it means a great deal. It is the difference between the part of the world that is ours to know and the part that is not. It makes the patch feel like home, and it makes us feel a little less crushingly insignificant. That is what the particle horizon is. That is what all our horizons are. The observable universe is our little patch of the plain, and its famous edge, the one you have seen illustrated in every documentary about the cosmos, is a picket fence, meaningless to the universe, precious to us. And what lies beyond the fence? By every measurement we can make, more plain. The temperature of the sky is astonishingly uniform in every direction we look, matching to about 1 part in 100,000, and the pattern of galaxies looks statistically the same no matter which way we point our instruments. Everything we can test supports what cosmologists call the cosmological principle, the working assumption that our patch is typical, that the universe beyond the horizon carries on much as it does here, with no wall, no thinning out, no sign of an approaching end. At an absolute minimum, simple geometry demands thousands of regions as large as our observable universe beyond our view. And if the universe is truly infinite, then the plane goes on without limit, patch after patch after patch, forever, each with its own fence, each fence centered on someone else. One more possibility deserves a word before we move on, because it is the one loophole in everything I just said. The universe could, in principle, be finite without having any wall, by wrapping around on itself in a way too large for us to notice, the way the screen of an old arcade game wraps, so that a ship exiting on the right reappears on the left. If the universe were wrapped like that on a scale smaller than our horizon, the sky would betray it. We would find repeating patterns, matched circles of temperature, printed on opposite sides of the heavens, the same ancient light, arriving at our telescopes from 2 directions at once. Astronomers have searched for those matched circles in the sky's oldest light, carefully, and found nothing. If the universe does wrap around, it does so on a scale larger than everything we can see. Whatever the truth beyond the fence, it is out of our view, and it intends to stay that way. Notice what has happened to the child's question. We went looking for the edge of the universe, and all we found were edges of our own seeing, fences that travel with the observer, boundaries made as much of us as of the cosmos. A horizon is real, but it is not an end. It cannot be what our question was asking about. If the universe truly has an edge worth the name, it is not going to be found by looking farther. It is going to depend on something more fundamental, on the overall shape of everything, on whether the plane itself is finite or infinite. And that, remarkably, is a question we can measure. The answer, it turns out, hangs on a single number, and the number keeps landing in the most tantalizing place it possibly could. Part 3. 3 shapes for everything. The question of whether the universe has a true edge now depends on its shape, and the remarkable thing is that the menu of possible shapes is short. When Einstein rewrote gravity in 1915, he turned geometry itself into a physical actor. Space, in general relativity, is not a passive stage. It bends, it stretches, it curves in response to what it contains. And when you apply his equations to a universe that looks, on the larger scales, roughly the same everywhere and in every direction, which is exactly what ours looks like, the mathematics permits precisely 3 families of shape, not dozens, 3. The first possibility is that space curves back on itself, what cosmologists call positive curvature. The way to picture it is to drop down a dimension. Think of the 2-dimensional surface of a sphere, like the surface of the Earth. That surface has a finite area, yet nowhere on it will you ever find an edge. Walk in a straight line for long enough, and you do not fall off the world. You come home, approaching your starting point from behind. A positively curved universe is the 3-dimensional version of that. Fly your spaceship in a perfectly straight line for long enough, and without ever turning, you return to the star you left. Geometry itself misbehaves in such a universe, at least by the standards you learned in school. Draw 2 parallel lines and follow them, and they do not stay parallel. They drift toward each other and eventually cross, the way 2 lines of longitude, parallel at the equator, meet at the poles. In such a universe, the total volume of space is finite. You could in principle count every galaxy, and yet there is no boundary anywhere. This is the one option that truly retires the edge question, and it is the option Einstein himself initially chose for the cosmos, precisely because it spared him the problem of infinity. The second possibility is that space is flat. Flat does not mean 2-dimensional, like a sheet of paper. It means that the familiar geometry of the classroom holds true at every scale. Parallel lines remain parallel forever. The angles of every triangle add up to exactly 180 degrees, and space extends without limit in every direction, on and on, without end. In the vocabulary of relativity, the idealized empty version of this universe is called Minkowski space, named for Hermann Minkowski, the mathematician who first understood that space and time are woven into a single 4-dimensional fabric. There is a lovely irony in his name being attached to it. Minkowski had been one of Einstein's professors in Zurich, and he remembered his student as a lazy dog who never bothered about mathematics at all. A few years later, that lazy dog produced special relativity, and it was Minkowski who saw what it truly meant. In 1908, he announced that space by itself and time by itself were doomed to fade away into mere shadows, and that only a union of the two would preserve an independent reality. He died just months later, at the age of 44, never knowing what his 4-dimensional fabric would become. The third possibility is the strangest, and it is the one I most need you to sit with tonight, because it will carry the entire second half of our story. Space could be negatively curved. The 2-dimensional picture this time is not a sphere, but a saddle, or if you prefer the snack aisle, the surface of a Pringle chip, a shape that curves up in one direction and down in the other, extended without end in every direction. On a saddle, geometry misbehaves in the opposite way from the sphere. Parallel lines do not converge. They spread apart, peeling away from each other faster and faster the farther you follow them. Triangles are skinny, their angles adding up to less than 180 degrees. And there is, in a precise sense we will explore later, more room in such a space than flatness would allow, more elbow room at every distance, as if the universe had been given extra territory to hide between the directions you already know. A negatively curved universe, like a flat one, goes on forever. These three shapes come with three names that will matter to us. The idealized positively curved universe is called de Sitter space, after the Dutch astronomer Willem de Sitter, who found it hiding in Einstein's equations in 1917, within months of the theory reaching him in wartime Holland. The flat one, as we said, is Minkowski space, and the negatively curved one carries what may be the least imaginative name in all of physics. Because it is the mirror opposite of de Sitter's universe, it is called anti-de Sitter space. Physicists, who apparently agree the name is terrible, abbreviate it to ADS, and from here on, so will I. Keep that abbreviation in your pocket. AD-S space looks, at this point in our story, like nothing more than a mathematical curiosity, an empty saddle-shaped toy universe that resembles ours not at all. By the end of tonight, it will be the setting for the strangest idea in modern physics. There is a detail about de Sitter's universe worth flagging now, because it will return near the end of our story. When de Sitter mailed his solution to Einstein, Einstein disliked it intensely, and his reason was almost philosophical. De Sitter had described a universe containing no matter whatsoever, utterly empty, and yet its space-time was not static. It expanded, exponentially, doubling and doubling again on a fixed rhythm, driven by geometry alone. Einstein felt a universe without matter should not be allowed to do anything so dramatic. History has been unkind to that instinct. A universe dominated by dark energy, which is what ours is steadily becoming, behaves more and more like de Sitter's empty runaway with every passing eon. His toy model, disliked at birth, appears to be our destination. So which of the three do we actually live in? This is not a matter of taste. Curvature is measurable. Draw a large enough triangle in space, measure its angles, and the answer tells you the shape of everything. Nature, generously, has drawn the triangle for us. The oldest light in the universe, released when the cosmos was a few 100,000 years old, is printed with spots and ripples whose true physical size cosmologists can calculate from first principles. Comparing that known size with the size we observe on the sky is a geometry test spanning the entire visible universe. Light that has crossed a positively curved cosmos makes the spots look larger, like objects seen through a magnifying lens. Negative curvature shrinks them. Flatness leaves them just so. The measurement has now been made with exquisite care, most recently by the Planck satellite, combined with enormous surveys of how galaxies cluster. The result is a number called the curvature parameter, and its measured value is 0.0007, with an uncertainty of about 0.0019. In plain language, the universe is flat to within about 0.1%, as flat as we have ever been able to test. If space curves at all, the scale of that curving is at minimum hundreds of times larger than the entire observable universe, and quite possibly far more. Our 93 billion light-year patch, our whole fenced plot with its 2 trillion galaxies, would be like a postage stamp on a balloon the size of a planet, far too small to reveal the bend. I want you to notice what a strange result that is. Of the 3 possible shapes, 1 is finite, and 2 are infinite, and our measurements have landed us exactly on the razor's edge between them, so close to perfectly flat that we cannot yet tell which side of the line we are on. There is also a quieter argument worth hearing, a statistical nudge rather than a proof. If universes of all 3 types exist somewhere in the wider scheme of things, the infinite ones contain infinitely more galaxies, infinitely more planets, and infinitely more listeners drifting off to videos like this one than the finite ones do. If you had to bet on where a randomly chosen observer finds themselves, the smart money says an infinite universe. You are probably one of its residents. So for the rest of tonight, let us take the hint. Let us assume the plane truly is unbounded, that space goes on without end, and face the question we have been circling since the first minute. The universe is infinite. There is no wall. And yet I promised you an edge. How do you put a boundary on something that has no end? The first serious attempt to answer that began not with the universe at all, but with the strangest objects in it, and with maps that kept lying to the people who drew them. Part 4. The maps that break. Maps have a failure mode that has nothing to do with the territory. Every flat map of the round Earth must lie somewhere, and the classic Mercator projection, the one that hung in your childhood classroom, lies most extravagantly at the poles. Greenland swells to the size of Africa, though in reality it is 14 times smaller, and at the poles themselves the map simply breaks. All the lines of longitude, spread comfortably apart at the equator, crowd together and converge to a single point, and the mathematics of the projection divides by zero. If you knew the Earth only through that map, you might conclude that something terrible happens at the North Pole, that distances become meaningless there, that the world itself comes to some kind of end at that converging point. Nothing of the sort is true. Stand at the North Pole, and you find ordinary ice, ordinary wind, an ordinary horizon. The catastrophe was never in the world. It was in the map. Physics spent 4 decades trapped inside exactly this mistake, and the story of how it escaped is the doorway to the edge of the universe, so it is worth telling with a little care. In 1916, within weeks of Einstein publishing General Relativity, a German physicist named Karl Schwarzschild, then serving on the Russian front of the First World War, solved the brand new equations exactly for the simplest interesting case, the gravity around a single compact mass. His solution described what we now call a black hole, though the name would not exist for another half-century, and the solution contained an alarm bell. At one particular radius, a specific distance from the center that depends on the mass, the mathematics appeared to detonate. Terms divided by zero, quantities marched off to infinity. Time, as written in his coordinates, seemed to freeze solid. That radius is what we now call the event horizon. Schwarzschild himself never lived to see any of the argument. He mailed his solution to Einstein from the front, where he was calculating artillery trajectories between bouts of a rare autoimmune disease he had contracted in the trenches, and he was dead within months, at the age of 42. Einstein presented the work to the Prussian Academy on his behalf, praising its elegance, never suspecting that the strange radius buried in it would consume the field for half a century. For roughly 40 years, much of the physics community, with Einstein himself among the doubters, read that alarm bell exactly the way our imaginary map reader read the North Pole. They took the breakdown in the equations to be a breakdown in reality, evidence that the horizon was a pathological place, or more comfortingly, that nature would never actually manufacture such an object, that stars would always find a way to avoid collapsing so far. The horizon was treated as a wall where physics ends. Remember that phrase, because tonight it is going to rhyme. A place where the numbers blow up. A boundary the mathematics cannot cross. It sounds exactly like an edge of the universe, and that is precisely what it was mistaken for. It helps to be clear about what a coordinate actually is, because the whole confusion turned on it. A coordinate system is nothing more than a scheme for labeling events, an agreement about how to assign numbers to where and when. The labels are human choices, and like all human choices, they can be made badly. Schwarzschild's time coordinate was, in effect, the time kept by a clock infinitely far from the black hole, and measured by that faraway clock, a falling object really does appear to slow and freeze at the horizon, its light stretching and dimming until it fades from view. Physicists of that era sometimes called the objects frozen stars for exactly this reason. But the falling object itself feels nothing of the sort. By its own clock, it crosses the horizon in a finite, ordinary stretch of time and continues inward. Two descriptions, one event, and the paradox dissolves once you realize that one of the clocks simply cannot see past a certain point. The map was reporting its own blindness as a property of the world. The escape came in stages, from people who learned to redraw the map. As early as 1924, the astronomer Arthur Eddington found an alternative coordinate system for Schwarzschild's geometry in which nothing special happens at the horizon at all, though he did not fully register what he had shown. In 1958, the American physicist David Finkelstein made the point unmistakable. He constructed coordinates that follow a beam of light falling inward, and in those coordinates, the light simply crosses the horizon, smoothly, at a definite moment, with no divergence, no frozen clocks, no drama whatsoever. The infinity that had frightened everyone for 4 decades was what physicists call a coordinate singularity. It was the North Pole problem. The territory was fine, the map was bad. And then, in 1960, came the full revelation. Martin Kruskal and George Sekares, working independently, each constructed what amounts to the master map of the Schwarzschild geometry. Their trick, and I want you to hold on to it because it is the seed of everything to come, was to stop treating space and time as separate ingredients and instead build new coordinates by blending them, fusing distance and duration into hybrid quantities that no clock or ruler measures directly, but that the geometry itself finds natural. In these blended coordinates, the whole space-time unfolds at once, inside and outside the horizon together, every region laid flat and visible, like a building shown in cutaway. The horizon revealed itself to be not a wall, but a one-way door. A surface light can cross inward, but never outward. And the map held one more surprise, which nobody had ordered. The fully extended geometry contained a second exterior region, another complete outside universe, joined to ours through the interior, in a non-traversable throat, a connection now called the Einstein-Rosen bridge, the mathematical ancestor of every wormhole in your favorite science fiction. Whether nature builds such doubled structures is another question entirely. The point is what the new map proved. The forbidding infinity at the horizon had been an artifact all along, a fold in a badly drawn chart. Something important had been learned that went far beyond black holes, and it is the lesson I want you to carry forward into the rest of tonight. When your equations blow up, when quantities race off to infinity, you face a genuine fork. Perhaps reality itself is doing something extreme there. Or perhaps your description has failed, and the infinity is an illusion of the coordinates, a Greenland swollen at the edge of the page. There is no general rule for telling which, and the only way to find out is to hunt for a better map. Physics had now defeated one famous infinity by that method. But notice the limit of the victory. The infinity at the event horizon was, in the end, a fake, an artificial infinity that better coordinates dissolved entirely. The harder problem still stood untouched, because the universe itself presents an infinity that no clever coordinates can dissolve, for the simple reason that it is not an error. If space goes on forever, as we are assuming tonight, then infinite distance is really out there. Infinitely far is not a flaw in anyone's map. It is the plain truth of the territory. And our question, the child's question, about what the edge of everything would look like, lives exactly there, at a distance no traveller, no signal, and seemingly no mathematics could ever reach. Here, then, is the state of play as it stood at the dawn of the 1960s. Relativists had learned to fuse space and time into new coordinates to suppress false infinities, a family of techniques that goes by the name compactification, the art of folding an unbounded expanse into a bounded description. They had used it to walk through the door of a black hole, and a young mathematician turned physicist in England who had grown up steeped in the geometry of perspective drawing, in the tricks by which Renaissance artists placed infinitely distant horizons at a finite height on a canvas, began to ask the audacious next question. If a bad infinity can be folded away, can a true infinity be folded in? Could you build coordinates that catch the actual edge of an infinite universe, the genuine article, infinitely far away, and draw it as a line on a finite page, without breaking the physics in the process? His name was Roger Penrose, and his answer changed what the word edge means in physics. What he found is where our story stops warming up and truly begins. Part 5. Folding Infinity onto a Page. In 1963, in a short paper published in the journal Physical Review Letters under the unassuming title Asymptotic Properties of Fields and Spacetimes, Roger Penrose did the thing that was supposed to be impossible. He drew the edge of an infinite universe. Not an approximation of it, not a suggestive sketch, a mathematically exact rendering, in which infinitely distant regions of spacetime, and the infinite past, and the infinite future, appear as definite lines and points on a finite diagram, close enough to touch. The technique he introduced is called conformal compactification, and if tonight has a single hinge, a single moment where the impossible becomes routine, this is it. Let me show you how it works, because the idea itself is something you can hold. Start with a space-time diagram, the physicist's standard picture, with space running horizontally and time running vertically, so that a motionless object traces a vertical line as time carries it upward, and a moving object traces a slanted one. Drawn naively, such a diagram of an infinite universe needs an infinite sheet of paper. Space runs off the page to the left and right forever. Time runs off the top and bottom forever. So Penrose changed the scale, and he changed it the way the Mercator map does, but run in reverse. The Mercator projection takes a finite globe and stretches its poles out to infinity. Penrose took infinite space-time and squeezed its far reaches inward, rescaling distances more and more aggressively the farther out you go, so that each successive step on the page covers far more territory than the last. Near the middle of the diagram, a centimeter might represent a light year. Farther out, that same centimeter represents 1 billion light years, then 1 trillion, the intervals nesting faster than any exponential, until the entire infinite expanse has been gathered in, and the boundary itself, the actual infinity, arrives at a finite line you can trace with your finger. It helps to picture the grid lines of the finished map, because they tell you where all the squeezing went. On the compressed diagram, the old moments of constant time survive as roughly horizontal contours, and fixed locations in space survive as roughly vertical ones. Near the center of the figure, the grid looks calm and evenly spaced, like ordinary graph paper. But follow it outward toward any edge, and the contours crowd together, bunching tighter and tighter, so that every additional step on the page leaps across more space and more time than the step before. The bunching never quite finishes, and that is the point. The boundary is where it would finish, the limit of the crowding, the place the contours are forever approaching. In the true universe, that limit lies infinitely far away and infinitely far ahead. On the page, it is simply the rim of the figure, an honest line, labeled and legal to touch. Now, you should be suspicious. You are allowed to squeeze a picture however you like, but wild rescaling usually destroys the information that made the picture worth drawing. Distort a portrait that aggressively, and you lose the face. Penrose's transformation, though, was engineered to protect the one thing that matters most in relativity. And here is where I need you to learn a single technical word, because the rest of tonight hangs on it. The transformation is conformal. A conformal transformation is one that may stretch and shrink distances as violently as it pleases, but preserves every angle. Where two paths cross on the true spacetime, they cross at exactly the same angle on the compressed map. Sizes are sacrificed. Shapes, locally, and every relationship of intersection survive perfectly. Keep that word close, conformal. It sounds like bookkeeping tonight, and by the end of the night it will sound like the possible secret of reality. Why do angles matter so much? Because in a space-time diagram, the most important information is not distance, but slope. The paths of light rays are conventionally drawn at 45 degrees, and the paths of everything slower than light, which means everything with mass, everything that is anyone, slope more steeply than that. The 45-degree line is the boundary between the reachable and the unreachable, the skeleton of cause and effect itself. Penrose tuned his compactification so that light rays cross the compressed map at exactly 45 degrees everywhere, without exception, and with that single choice, the diagram stops being a picture and becomes an instrument. Any question of the form, can a signal from this event ever reach that one? Can this observer ever influence that region? Is settled on a Penrose diagram with a ruler. If you can connect the 2 points with a line at 45 degrees or steeper, the answer is yes. If you cannot, the answer is no, and no future technology will ever change it. Causality, the underlying grammar of the universe, is preserved intact on a sheet of paper that also, casually, includes the infinite past, the infinite future, and infinite distance among its features. I want to give you a feeling for what this object is like, so let yourself see it. You are floating in darkness, and before you hangs the whole of space-time, drawn as an endless luminous plane, crossed by the faint lines of every light ray and every wandering particle since the beginning. Now the folding begins. Nothing moves in the world itself. What changes is measure, the meaning of each step. The far reaches, a billion light-years of them, glide inward and settle into a hand's width of the picture. Distances a million times greater follow, arriving from farther than any telescope has seen, each new infinity of territory, accepting a thinner and thinner margin of the page, and the remote past rises from below, while the remote future descends gently from above. Watch the light rays as it all comes in. Every other line bends and crowds under the compression, but the light holds its angle, 45 degrees, incorruptible, a lattice of perfect diagonals steadying the whole collapse. And then it is done. Where an infinite universe sprawled, there now floats a single closed figure, a diamond of finished light, its edges sharp, its interior holding every event that has ever happened or ever will. You could reach out and cover eternity with your palm. Nothing has been left out. It is all there, complete, and quiet, and small. That diamond is the Penrose diagram of flat spacetime, and versions of it, decorated with the geometry of black holes and expanding universes, now fill the whiteboards of every relativity group on Earth. The diagrams earn their keep most famously with black holes. Draw the Schwarzschild geometry the Penrose way, and the event horizon, that surface which confused the best minds in physics for 40 years, appears as a clean line at exactly 45 degrees, the same slope as light itself. Suddenly the horizon's whole character is visible at a glance. It runs parallel to the escape routes. A signal emitted just outside can climb away to safety, but a signal from just inside, however fierce its engine, would need to travel shallower than 45 degrees to get out, and nothing in this universe is permitted to do that. Every debate about whether things can escape a black hole, decades of confusion in the old coordinates, collapses into one look at one diagram. That is what a good map does. It turns paradoxes into geometry. The construction was refined in those same years by the physicist Brandon Carter, which is why you will also hear these figures called Penrose-Carter diagrams, and using them fluently is simply part of what it means to be trained in general relativity today. There is a pleasing origin story in the background. Penrose came to physics soaked in the tradition of projective geometry, the mathematics that grew out of Renaissance perspective drawing. the discovery by artists that you could place the infinitely distant on a canvas, that parallel roads could be drawn meeting at a vanishing point, and the eye would read it as truth. A vanishing point is infinity, tamed by a rule of drawing. Penrose's diagrams are, in a precise sense, the physics-grade descendant of that trick, the vanishing point made rigorous, with a theorem where the painter had a habit. Now for the caution, and I will plant it here deliberately, like a seed, because we are going to dig it up again much later tonight, in very different light. You know the old proverb, the map is not the territory. A drawing of the sea is not wet, a menu is not a meal, and a diagram of infinity, however exact, is presumably not the thing itself. The boundary line around Penrose's diamond, on this way of thinking, is a representational convenience, a bookkeeping edge, real in the way the equator is real, which is to say real as an idea, but not a place where anything is. That is the sensible, sober, obvious position. I ask only that you notice tonight, as the evidence accumulates, how much work that boundary starts doing, how physics leans on it, measures things at it, defines things by it. Hold the proverb and watch the edge. One of them is going to give. Because here is what changes everything. When you compactify space-time the way Penrose did, the boundary you produce is not a single featureless line, a mere frame around the picture. Looked at closely, the edge of the diamond resolves into distinct pieces, different kinds of infinity, with different characters, different residents, and different laws about who may arrive. The edge of an infinite universe, it turns out, has an anatomy, and the strangest of its organs is reserved for light alone. Part 6. The Anatomy of the Edge. The edge of the diamond is not one place. Look closely at the boundary of Penrose's compressed universe, and it separates, under your attention, into 5 distinct pieces, 5 different kinds of infinity, each with its own name, its own character, and its own strict guest list. This is the moment tonight where the phrase edge of the universe stops being a metaphor and acquires an anatomy. So let us walk the boundary together, piece by piece, the way you might walk the walls of an old city. Start at the bottom of the diamond, at its lowest point. That single point is called past time-like infinity, and it is the bottomless past, the limit of every history traced backward without end. Here is the first strange rule of the anatomy. Every object with mass, every particle that moves slower than light, which means every atom, every star, every person, traces a path on the diagram steeper than 45 degrees, and if you follow any such path backward far enough, it funnels down into that one point at the bottom. All matter on the diagram emerges from there, as if the entire population of an infinite universe had been poured in through a single opening. Its mirror twin sits at the top of the diamond, the highest point, called future time-like infinity, and it is where every one of those paths, followed forward forever, must finally converge. Whatever wanders, whatever orbits, whatever flees, if it has mass, its path bends inevitably home to that summit. One point where all matter begins, one point where all matter ends. On the true, uncompressed universe, these are not places at all, only directions of endless time, but on the map, they are as definite as capital cities. Out at the left and right corners of the diamond sits the third piece, space-like infinity, the limit of infinite distance at a single frozen moment. It is the infinity the child's question always pointed toward, the farthest far away, the end of the yardstick. And here is the quiet joke the geometry plays. Nothing ever goes there. No path of matter, no ray of light ever arrives at space-like infinity, because to reach infinite distance in finite time is exactly what the 45-degree law forbids. The destination the question dreamed of, the place a spear would strike, turns out to be the one part of the edge that nothing in the history of the universe will ever visit. It sits in the corners of the map like a city on old charts marked but never entered. Which leaves the diagonals, and the diagonals are where the anatomy becomes beautiful. The two sloping sides at the bottom of the diamond and the two at the top are called past null infinity and future null infinity. Null is the relativist's word for the paths light takes, and these boundaries belong to light completely. Physicists write each of them with a single elegant symbol, a flowing script letter I, and pronounce it scree, a small piece of professional poetry, the sound of the pen catching up to the universe. Every ray of light in the cosmos, traced back to its ultimate origin, comes in through past null infinity. Every ray that escapes every star and every collision, traced forward forever, lands on future null infinity. Light is born on one diagonal of the universe and dies on the other, and nothing slower may touch either one. A rocket can chase a departing light ray for 1 trillion years and will find itself, on the map, pulled up the steepening curve toward the summit where all matter must go, while the light slides away along its perfect diagonal to a boundary the rocket can never reach. Here is a law worth saying plainly, because we will need it again before the night ends. Matter never reaches the edge of the universe. Only light can touch it. One refinement is worth savoring before we move on. When mathematicians examine the assembled boundary as a single object, they find that it is not just a frame drawn around space-time. It has a geometry of its own, and that geometry is null, the geometry of light. The edge of flat space-time is itself woven from the same fabric as the light rays that terminate on it, a boundary made not of place, but of pure propagation. There is something almost too fitting in that. The only things able to reach the edge of the universe are rays of light, and when they arrive, they find a shoreline built of the same substance as themselves. I want you to ride that journey once, and you are allowed, because tonight you can be a photon. You are emitted, this instant, from the surface of a dying star. For you there is no waiting, because at the speed of light no time passes at all. But watch the map instead of the clock. Your path is a flawless diagonal, 45 degrees, and it will hold that angle across the entire remaining history of the universe. Around you, the paths of matter rise like slow smoke, curving upward, growing steeper, every galaxy and every stone bending toward the summit point, where all massive things are gathered in the end. You do not bend. Galaxies drift past you and recede. The crowded regions of the map thin out. The contours around you bunch tighter and tighter as the page runs out, each of your strides now spanning ages of the world, and still your angle holds, and ahead of you, no longer distant, is the sloping line itself, the upper diagonal, the retirement of all light. You arrive, not at a wall, not at a barrier, but at the completed edge of everything, the one destination in the geometry reserved for things like you. Every photon that has ever escaped every candle and every quasar is arriving here too, each at its own point along the line, the whole electromagnetic history of the universe filed neatly along one luminous border. And if anyone still doubts whether that border is real enough to matter, stay with me, because within a few minutes we will watch it hold up the most famous calculation of the 20th century. Step back now and look at what is on the page. A diamond, 2 fingers of ink, and by construction, nothing left out. Every event that has ever occurred, or ever will, in an infinite universe across infinite time, has its point inside that figure. The birth of the first star is in there. The cooling of the last one is in there. Every life, including the one you are living tonight, every thought anyone will ever think, occupies its own small neighborhood of the interior, at scales far too fine to draw but present, accounted for, enclosed. You could lay your palm flat over the diagram and cover eternity. I find it worth sitting with the fact that this is not a gesture or an artwork, but a working scientific instrument, as literal as an anatomy chart. Infinity was never too large to draw. We had simply not yet learned the projection, The child asking what is at the edge of everything was not asking a broken question. The question was waiting, all along, for a better map. A different future is worth one sentence here, planted for later. Our own universe, with its dark energy and its accelerating expansion, is not quite the asymptotically flat diamond we have been drawing tonight. And when you construct the honest diagram for a universe like ours, the boundary changes character in a way that will matter enormously at the end of this story. File that away. The shape of the edge depends on the universe it encloses, and ours has a surprise waiting there. There is one more feature of the anatomy to install before we put it to work, and it is the feature that turns the boundary from a marvel into a tool. Penrose diagrams describe universes that are what physicists call asymptotically flat, meaning that whatever chaos fills the interior, however violently mass may curve the middle of the map, the geometry settles down toward flatness as you approach the boundary. Out near the edge, space-time becomes simple, calm, and clean, the pure, unbent arena of special relativity. That has a wonderful consequence. Some of the most basic quantities in physics, which are surprisingly slippery to define inside a curved and churning space-time, become sharp and rigorous if you measure them from the boundary. The total mass of an isolated system is defined there, at infinity, by how space-time settles toward the edge. And when physicists were tangled for decades in a dispute about whether gravitational waves were physically real or a mathematical mirage, the argument was finally settled at future null infinity, where one can prove that a system shedding gravitational waves loses mass as they cross the boundary, carrying energy that is unmistakably real. The edge, in other words, is where some of physics bookkeeping is actually kept, which raises an irresistible thought. If the boundary at infinity is solid enough to define mass and energy, could you stand on it and discover something new? In 1973, a physicist in Cambridge, newly confined to a wheelchair and slowly losing the use of his hands, decided to find out. Part 7. The Edge Gets a Job. Stephen Hawking, in the early 1970s, was a young Cambridge physicist with a progressing motor neuron disease, a specialty in the global geometry of spacetime, and a grudge worth telling. A Princeton graduate student named Jacob Bekenstein had recently proposed something that struck Hawking as close to nonsense. Bekenstein argued that a black hole must carry entropy, a genuine thermodynamic bookkeeping of hidden information, and that this entropy should be proportional to the surface area of its horizon. Hawking thought the idea confused a mathematical analogy for physics, and he set out, in part, to put it to rest. What he found instead did not put Bekenstein to rest. It vindicated him, transformed him from a doubted student into a prophet, and handed physics the clue it would chew on for the next 50 years. And the reason the discovery was possible at all, the quiet foundation under the whole celebrated result, was the boundary at infinity we have just finished building. Here is the problem Hawking faced, stated plainly. He wanted to ask what quantum field theory, the physics of particles and their fields, does in the neighborhood of a black hole. But quantum field theory has a temperamental relationship with curved spacetime. In particular, the theory's most basic notion, the vacuum, the state of a field when nothing is present, is only cleanly defined in flat spacetime. That sounds like a technicality, so let me give it some weight, because it is one of the strangest facts in physics. In quantum theory, empty space is not empty. Every field seethes at all times with irreducible fluctuation, a restless static that cannot be stilled, and what an observer counts as a particle turns out to depend on the observer's own state of motion. The vacuum is not a thing that sits there, it is a judgment call, and in a strongly curved, evolving spacetime, different judges disagree, and there is often no principled way to crown one of them. Only in flat spacetime do all the natural judges agree on what nothing looks like. If you want an honest definition of emptiness, you must go where spacetime is flat, and where, in a universe that contains a black hole, Is space-time honestly flat? You know the answer, because we built it in the last part, at the boundary. In an asymptotically flat universe, the curvature of any star or black hole dies away with distance, and the geometry near the conformal boundary settles into the pure, unbent flatness where quantum field theory behaves. The infinities of the Penrose diagram are not just philosophically clean, they are the only rigorously trustworthy laboratory in the entire space-time. So Hawking set up his calculation as a conversation between two infinities. At past null infinity, before the star collapses, he defined his quantum field to be in a perfect vacuum, genuinely empty by the one definition everyone must accept. Then he let the field propagate forward through the space-time, through the era in which the star collapses and the horizon forms, and he asked one question at future null infinity, out at the far shore of the future where flatness returns. Is the field still empty there? The answer was no. What arrives at future null infinity is not the vacuum. It is a steady, endless flux of particles, streaming outward from the direction of the black hole, and when Hawking computed the energies of those particles, they matched, exactly, the spectrum of ordinary thermal radiation, the glow of a hot object, with a definite temperature set by nothing except the black hole's mass. The black hole, the perfect one-way absorber, the object defined by the impossibility of escape, shines. It shines the way an ember shines, patiently converting its own mass into a dim, outgoing glow, and given unimaginable spans of time, that glow carries the entire black hole away. The result stunned Hawking himself, who spent months trying to find his own mistake before publishing, in 1974, under a title with a question mark in it, Black Hole Explosions ? As if even the journal article was not quite sure it believed itself. The temperature deserves numbers, because the numbers are part of the poetry. For a black hole with the mass of our sun, Hawking's formula gives a temperature of about 60 billionths of 1 degree above absolute zero, so cold that the black hole is chillier than the faint afterglow of the Big Bang that fills all of space. Today, such a black hole absorbs more warmth from the sky than it gives back, and it will not even begin its true evaporation until the universe has aged and cooled for eons beyond the present. Once the shrinking starts in earnest, the timescale for a solar mass black hole to radiate itself entirely away runs to roughly 10 to the power of 67 years, a number so far beyond the current age of the universe that comparing them is barely meaningful. None of that slowness ever mattered to physics. What mattered was the principle. The glow is real, the temperature is exact, and Hawking valued the result above everything else he ever did. The formula for it is carved on his memorial stone in Westminster Abbey, where he was laid between Newton and Darwin, a temperature measured at the edge of the universe, resting now in the floor of a church. Two features of this discovery matter for our road tonight. The first is what it did for Bekenstein. With a real temperature in hand, the thermodynamics locked into place, and the entropy Bekenstein had guessed at could be computed exactly. A black hole's entropy equals 1/4 of its horizon's surface area, measured in the smallest units of area nature allows. The Planck scale, the floor of reality we have visited on this channel before. Hold that sentence up to the light, because something is wrong with it, magnificently wrong. Everywhere else in physics, entropy, which counts the information a system can hide, grows with volume. A bigger library holds more books because it encloses more shelf space, more interior. But a black hole's capacity for hidden information grows with its area, with the size of its wrapping, as if the books were stored not in the library, but on its outer wall, as if the interior, the entire three-dimensional inside, contributed nothing at all. Nature's densest information storage counts surface, not volume. Almost nobody in 1974 grasped how far that clue would eventually lead, and I will ask you to keep it glowing quietly in the back of your mind, because it is the seed of everything in the last hour of tonight. The second feature is the one this night is really about, and it is hiding in the shape of the argument itself. Look at where the calculation lives. The vacuum was defined at one infinity. The radiation was detected, on paper, at the other. The famous temperature is, strictly speaking, the temperature that an observer, infinitely far away, sitting at the conformal boundary in the flat calm at the end of the map, would measure. The most celebrated result of late 20th century physics is, in its rigorous form, a statement about the edge of an infinite universe, derived by a man who found a way to stand there, twice, once in the remote past and once in the remote future, and compare notes. The boundary Penrose drew as a mathematical convenience had become a load-bearing wall. Physics was now measuring real things from a place that does not, in the ordinary sense, exist. Let us take a slow breath and stack the ladder we have climbed, because we have come a long way from the picket fence, and the next rung is the strange one. We began with horizons, the personal fences of visibility, real but observer-made, edges of view and not of world. We learned the universe has three possible shapes, and that ours sits on the knife edge of flat, with infinity the statistical favorite. We watched physics mistake a bad map for a wall for 40 years, then learned to redraw its maps so well that even true infinity could be folded onto a page with every angle intact. We found that folded edge has an anatomy, 5 infinities with 5 characters, and a strict rule: matter never touches the boundary, only light is allowed to arrive. And now we have watched the boundary earn wages, anchoring the calculation that taught us black holes glow, and that information, somehow, lives on surfaces. All of that, and one fact remains stubbornly true: the boundary of flat spacetime, for all its power, is a place only mathematics visits. Nothing comes back from it. It cannot signal, cannot answer, cannot participate. If the edge of the universe is ever to be more than a ledger at the end of time, we need a universe whose infinity leans closer. A geometry whose boundary is not a silent shore, but a living wall. That geometry exists. You have seen it, almost certainly, hanging framed on a wall, in a woodcut of angels and devils, drawn by a man who insisted he understood no mathematics at all. Part 8. The geometry with too much room. Every geometry you were taught in school rests on 5 assumptions, and for more than 2,000 years, one of them refused to sit still. Euclid, organizing all of geometry around 3 centuries before the Common Era, founded the subject on 5 postulates, and the first 4 are the kind of statement nobody loses sleep over: that you can draw a line between any 2 points, that circles exist, and so on. The 5th is different. In its most useful form it says this: given a line, and a point not on that line, there is exactly one line through the point that never meets the first, one and only one parallel. It sounds obvious. It is the geometry of every tiled floor and every sheet of graph paper you have ever seen. But it never felt like the others, even to Euclid, who visibly avoided using it for as long as he could. For 20 centuries, mathematicians tried to prove it from the first 4 postulates, to show it was not an assumption at all, but a consequence, and for 20 centuries they failed, and some of them ruined their lives on it. The ones who finally broke through did it by committing what felt like a sin. Instead of proving the 5th postulate, they denied it, assumed a world where through that outside point there run many parallels to the given line, infinitely many, and then followed the consequences, waiting for the contradiction that would reward their patience and rescue Euclid. The contradiction never came. What came instead was geometry, page after page of it, alien but flawless, triangles whose angles sum to less than 180 degrees, parallel lines that spread apart forever, a complete and self-consistent description of a space that behaves like an endless saddle. A young Hungarian officer named János Bolyai wrote it up around 1832, publishing it as an appendix to his father's textbook. His father, a mathematician himself, had begged him in a famous letter to abandon the problem, writing that the science of parallels was a bottomless night that had swallowed his own life's light and joy, and pleading, "For God's sake, give it up." Janos did not give it up, and when the work was done, he wrote back the most defiant sentence in the history of mathematics: "Out of nothing I have created a strange new universe." Unknown to him, a Russian mathematician, Nikolai Lobachevsky, had published essentially the same strange universe 3 years earlier in Kazan, to indifference and mockery. And unknown to both, the greatest mathematician alive, Carl Friedrich Gauss, had worked much of it out privately decades before and locked it in his desk, confessing to a friend that he feared the clamour of the Boeotians, the howling of small minds, if he ever dared print it. When Bolyai learned that Gauss had been there first, and later that Lobachevsky had published first, something in him broke, and one of the great creators of the subject never published mathematics again. For a generation, this hyperbolic geometry, as it came to be called, hung in limbo, consistent seeming, but unproven, a possible impossibility. Then in 1868, an Italian mathematician, Eugenio Beltrami, closed the question with an idea that has since become one of the master tools of all mathematics. He built models. He showed that you can construct, inside perfectly ordinary Euclidean space, exact working replicas of the hyperbolic world, dictionaries in which every hyperbolic concept is translated into a Euclidean one, so that any contradiction lurking in the new geometry would translate into a contradiction in the old. The saddle world is exactly as trustworthy as the floor tile world. If hyperbolic geometry ever falls, it takes Euclid down with it. Beltrami's first replica, before the disk, was a physical surface you could set on a table, a trumpet-shaped figure called the pseudosphere, curving away from itself at every point at a perfectly constant rate, the saddle's curvature made solid. It captures only a patch of the hyperbolic plane, not the whole, but it made the abstraction touchable, and it settled nerves. The strange new universe was not a fever dream. You could cast it in plaster. And among the models that emerged from this era, one is so perfect, so useful, and eventually so famous, that it belongs to the story of the edge of the universe. It is called the Poincaré disk, after Henri Poincaré, the French polymath who made it celebrated in the 1880s. Here is the construction, and notice how familiar it is going to feel. Take the entire infinite hyperbolic plane, the whole endless saddle, and map all of it into the interior of a single finite circle. Out at the middle of the disk, the map is gentle, and shapes look much as they should. But as you move toward the rim, the map compresses, scales shrinking faster and faster, each millimeter of the page representing more and more of the saddle, without limit, so that the boundary circle itself corresponds to infinite distance. No point inside the disk is infinitely far from any other. The rim is infinitely far from all of them. Straight lines, the geodesics of the saddle, appear on the disk as arcs of circles that meet the boundary at exactly 90 degrees, and through any point you can fan out infinitely many such arcs that never cross a given one. The many parallels the founders dreamed of, drawn plainly. And the map is conformal. There is our word again, and it is no coincidence. Sizes on the Poincaré disk are sacrificed without mercy, but every angle is preserved exactly, every crossing faithful. It is the Penrose construction's older sibling, discovered decades earlier, an infinite world folded into a finite figure, with its angular truth intact. Penrose compactified space-time. Poincaré had already compactified space, and the space he compactified was the saddle. One measure of how much world is packed inside that little circle is worth feeling in your bones. In flat space, when you double the radius of a circle, its circumference doubles. Room grows in proportion. In hyperbolic space, room grows exponentially. Walk 1 mile out from your front door in the saddle world, and there is more circumference around you than flatness would allow. Walk 10 miles, and the surplus is overwhelming. territory multiplying beyond all proportion, so that the region within a modest stroll of your house contains more area than a flat country the size of a continent. Hyperbolic space is the geometry with too much room, elbow space beyond any Euclidean accounting at every scale, and all of it, every exponential acre, fits inside the disk, paid for by shrinkage near the rim. Mathematicians even crochet the stuff. If you increase stitches at a steady exponential rate, row after row, the yarn has no choice but to ruffle and flare into a physical model of the hyperbolic plane, a technique introduced by the mathematician Dana Taimina in the late 1990s, and the frilled, endlessly crinkling result is also, not coincidentally, the shape of coral and curly kale, nature's own experiments in fitting too much surface into too little space. Before we go on, remember why we are here, because this has not been a detour. Our question tonight is what the edge of an infinite universe would look like, and the hyperbolic plane is the first infinite world we have met, whose edge you can simply look at. The rim of the Poincaré disk is a genuine boundary at infinity, the whole of it visible at once, drawn as an honest circle. And recall the third of the three possible shapes for a universe, the negatively curved option, the infinite saddle, the one I asked you to keep in your pocket under the name add S. The geometry we have just learned to fold into a circle is that universe's spatial fabric. We are, quietly, assembling the stage on which the strangest act of tonight will be performed. The saddle world's abundance shows up in one more register that will matter shortly. Ask how many ways you can tile a geometry with identical regular shapes, edge to edge, no gaps. On the sphere, the answer is 5, the famous Platonic patterns. On the flat plane, it is exactly 3, triangles, squares, hexagons, the eternal bathroom floors. On the hyperbolic plane, the answer is infinite. Infinitely many regular tilings, pentagons meeting 4 to a corner, heptagons meeting 3 to a corner, patterns without end. Because the exponential surplus of room means polygons can always find space to close around a vertex in new combinations. Whole families of order that flat space is too cramped to permit flourish on the saddle. And in 1957, a figure showing one of those impossible tilings, drawn in the Poincaré disk, was mailed from a geometer in Toronto to a graphic artist in the Netherlands, a man then approaching 60 who had spent years hunting, with growing desperation, for a way to draw infinity inside a finite frame. He opened the envelope, and the hunt was over. Part 9. The Artist Who Drew Infinity. Moritz Cornelis Escher spent the middle of the 20th century trying to draw something no artist had ever captured, and failing, and knowing exactly why he was failing. The Dutch printmaker had become famous for his impossible staircases and self-drawing hands, but his private obsession, the one he returned to for decades, was infinity. Not the suggestion of infinity, not a road dwindling toward a horizon, which any competent draftsman can manage. He wanted the real thing, an infinite multitude, complete and entire, held inside a finite picture. His instinct was tessellation, the interlocking repetition of a single figure, a craft he had fallen in love with as a young man studying the Moorish tilings of the Alhambra in Spain. He filled notebooks with interlocking birds, fish, and lizards, and he understood the arithmetic of his problem with total clarity. A repeating pattern on a flat page can go on forever, but only by leaving the page. To trap all of infinity inside the frame, the figures would have to shrink as they multiplied, endlessly, towards some boundary, without ever quite reaching it, and every scheme he devised for shrinking them, and he tried for years, bent the figures out of true, or collapsed the pattern into a smear at the center or the rim. He could feel that the solution existed. He could not construct it. He did not know that mathematicians had constructed it 70 years before he needed it. The envelope arrived in 1957. Escher had met the geometer, Harold Coxeter, one of the great masters of symmetry, at a mathematical congress in Amsterdam 3 years earlier, and the two had struck up a friendly correspondence. Coxeter sent him a paper on symmetry, and somewhere in its pages, included almost incidentally as an illustration, was a figure showing a regular tiling of the hyperbolic plane, drawn in the Poincaré disk, triangles repeating inward from the center and dwindling toward the rim in flawless, angle-true recession, infinitely many of them, all inside one circle. Escher wrote back that the figure had given him quite a shock. He said it in English, underlined, in a letter otherwise written in Dutch. Decades of groping, and here was the answer, drawn by strangers for entirely other reasons, sitting in the mathematical literature since before he was born, waiting for the one artist on earth who had spent his life preparing to need it. He did not understand the underlying theory, and he said so plainly. He did not need to. He was, in his own phrase, absolutely dependent on what he could see, and now he had seen it. He took a ruler and compasses to Coxeter's figure, reverse-engineered the scaffolding of arcs beneath it, and got to work on the series he would call the circle limits. The correspondence between the two men has its own gentle comedy, worth a moment, because it says something about how understanding travels. Escher, wrestling with the finer construction of the arcs, wrote to Coxeter asking for practical help, a simple recipe, and Coxeter replied with pages of professional mathematics, references, symmetry groups, the works. Escher complained to his son that the answer was, in his words, so much hocus pocus to him, and that nothing in it helped him cut wood. He needed the how, not the why, and in the end he extracted the how himself, with drafting tools, from the picture alone. 2 men, 1 subject, no shared language beyond a figure in ink, and between them they moved the boundary of infinity, from the journals to the living room wall. Coxeter, to his lasting credit, understood exactly what had happened, and spent years afterward lecturing delightedly on the mathematics hidden in his friend's prints. Between 1958 and 1960, he produced 4 of them, cut by hand into blocks of wood, printed in his studio. Circle Limit 1, interlocking fish, stiff and experimental, a proof that the machinery worked. Circle Limit 3, the masterpiece of the series in most eyes, golden and blue fish streaming along white arcs like traffic on curving boulevards, a print requiring 5 separate woodblocks and 4 printings each rotated into place. And in 1960, Circle Limit 4, the one the world knows, called Heaven and Hell, in which winged angels and bat-winged devils interlock perfectly, each the exact negative shape of the other, filling the disk from its center outward, in ring upon ring, halving and halving again. Dozens of figures, then hundreds, then figures smaller than commas, then figures at the rim finer than any blade could cut, the pattern converging on the boundary circle where, in the logic of the print, infinitely many angels and infinitely many devils crowd into edges thinner than existence. It hangs now in dorm rooms and mathematics departments and living rooms on every continent, and most of the people who love it have never been told what they are actually looking at. It is a conformally compactified infinite universe. It is the same species of object as Penrose's diamond, built on the identical mathematical spine, the boundary at infinity rendered as an inked circle, a hand's width across. The most widely reproduced image of the edge of an infinite world was printed from pearwood by a 61-year-old craftsman who insisted to the end that he was no mathematician. And here is the fact about the print that I find genuinely moving. In the world the woodcut depicts, the shrinking is an illusion of the map. Hyperbolic space is perfectly homogeneous, the same at every point, and every angel in Circle Limit 4 is, in the geometry it inhabits, exactly the same size as every other. The tiny figures near the rim are not far away in some picturesque distance, and they are not miniatures. They are full-sized residents of a world with too much room, drawn small only because our flat page must pay for their world's exponential abundance somehow. and it pays at the rim. Years later, Coxeter went over the prints with a mathematician's instruments and published his verdict. The arcs of circle limit 3, constructed by eye and compass from one borrowed figure, are accurate to a few thousandths. Escher got it absolutely right, he wrote, with the particular admiration of a man watching a foreigner speak his language without an accent. Escher, for his part, wrote of these prints that he was closing a cycle, sealing infinity inside a circumference, and that the beauty of the enterprise lay in the fact that it could actually be finished. A human being had set out to complete an image of the infinite and had completed it. Keep our night's question in view as you look at the print, because the print sharpens it wonderfully. Here is an infinite world whose boundary is not off the page, not implied, not gestured at, but drawn, a completed circle enclosing endlessness. If a universe were built on this geometry, its edge would not be a mystery beyond the horizon. It would be a visible fixture of the sky of mathematics, the same circle from everywhere, infinitely far from everyone. What remains is to ask what that circle would be like as physics rather than as ink. Step into the print for a moment. You stand at the center of the disk, and the angels and devils around you are the size of people, and the rim of the world is a dark circle on the horizon of your sight, seemingly a day's walk away at most. So walk. The first ring of figures passes easily, but something is quietly wrong with your progress, because the figures ahead, which looked small, are person-sized when you reach them, every ring the same, and the rim has not come closer. You walk for hours. The tiles keep their promise, each as large as the last when you arrive, the pattern repeating with the same angles, the same meetings of wingtips, and behind you, the center of the world has receded into haze, while ahead the boundary stands exactly where it stood. You could walk for years like this. You could walk forever, and the accounting would never change. Full-sized country after full-sized country, and the dark rim patient beyond all of it, unapproached and unapproachable. You live inside an infinity. You can see its edge from every point in the world, and you can never, ever touch it. Now you know what the edge of an infinite universe looks like from inside, at least in a single frozen instant. But a universe is not a frozen instant. A universe has time, moment following moment, and the question that has been waiting all night is what happens when you give this disk a clock, when you let its infinity breathe. The answer is that the disk becomes a cylinder, and its edge stops being a picture and starts being a place. Part 10. The box with its wall at infinity. Time enters the picture the way it always does in relativity, as another dimension of the diagram. Take Escher's disk, or rather the clean Poincaré disk beneath it, and let it represent all of an infinite two-dimensional hyperbolic universe at one single instant. Now stack such disks, one atop another, each disk the same universe a moment later, an unbroken column of instants rising without end, the way a film strip stacks frames into a motion picture. What you have built is a cylinder, infinitely tall, and it is not a metaphor. That cylinder is the exact textbook picture of a space-time called anti-de Sitter space, the third of our three shapes, the saddle universe, the one we agreed to call Ad-S. The interior of the cylinder, all the stacked disk interiors together, is the universe itself, and physicists call it the bulk. 2 dimensions of space, one of time, an infinite negatively curved cosmos, evolving moment by moment, and the surface of the cylinder, the stacked rims of all the disks, is the boundary at infinity, the circle limit rim, given a history, extended through time, into a wall. Every point of that wall is infinitely far from every event inside, and that wall is about to become the main character of the night. Because here is the sentence this entire evening has been assembling, and I want to deliver it slowly, in pieces, so that you feel it locked together. The rim of a single disk is a circle, which is a one-dimensional space. Sweep that circle through time, up the cylinder, and the wall acquires a second dimension, duration. One dimension of space, plus one of time. And what is a space-time, with dimensions of space and time, and no curvature to trouble it? It is flat space-time. It is Minkowski space, the first and simplest universe we met tonight. Say it in full. The boundary of a conformally compactified anti-de Sitter universe is itself a complete, conformally compactified flat universe with one fewer dimension. The edge of this infinite universe is not a wall, not a membrane, not a mathematical residue. The edge of this infinite universe is another universe, a smaller sibling, one dimension slimmer, wrapped around the bulk the way a label wraps a bottle, possessing everything a universe needs: space, time, and room for physics to happen in, and the construction scales without complaint. Model a three-dimensional hyperbolic space inside a sphere, the Poincaré ball. Stack the balls through time, and the boundary of that four-dimensional bulk is a flat universe with 3 dimensions of space and 1 of time, which you may recognize as the shape of the universe you believe you are sitting in right now. I will let that observation lie there, unexploded, for a little while longer. If the boundary were merely adjacent, this would be a curiosity. What makes ADS the strangest and most consequential geometry in modern physics is how the bulk and its boundary talk. Recall that in flat spacetime, the edge at infinity is a silent shore. Light departs toward it and never reports back, and nothing that happens there, so to speak, could ever matter here. Anti-de Sitter space rewrites that rule, and the rewriting comes from the curvature itself. Negative curvature acts on motion the way a steepening valley acts on a rolled ball. It confines. Throw a massive object outward, toward the infinitely distant wall, as hard as you please, and the geometry taxes its progress, slowing it, exhausting it, until at some finite distance it halts, turns, and falls back to you, like a ball tossed up a hillside that steepens without end. Matter in ADS is a permanent resident of the interior. It cannot approach the edge, not merely in practice, but in principle, confirming the law we learned on the diamond. Matter never touches the boundary of the universe. But light, once again, is the exception, and in ADS, its exceptional status becomes almost unbelievable. Aim a light ray at the wall at infinity, and the same compounding geometry that taxes matter subsidizes light. The ray crosses the infinite distance, touches the boundary, and returns to your hand, and the entire round trip, out to infinity and home again, takes a finite time by your watch. Not approximately finite, exactly finite, a fixed interval, set by the curvature of the universe, the same for every such trip, as regular as a pendulum. 2 properties of this confining geometry are worth adding to your picture of the place. The first is that ADS solves Einstein's equations with a negative cosmological constant, a vacuum whose intrinsic energy pulls inward rather than pushing outward, the exact mirror of the dark energy inflating our own cosmos, which is the first hint, filed for later, that this marvelous box may not be the universe we live in. The second is stranger and lovelier, because every thrown stone in ADS returns on a timetable set by the curvature alone, not by the strength of the throw. The entire universe has a single natural rhythm, one universal period, on which all its wandering matter oscillates, every orbit and every toss keeping the same great beat. Anti-de Sitter space does not just confine its contents. It keeps time for them, a cosmos with the temperament of a struck bell. Sit with the daily life of that universe for a moment, because you can. You stand in an endless saddle-shaped cosmos, tiles of identical country stretching away from you forever in every direction, and you hold a stone and a lamp. You throw the stone outward, at the edge of everything, with all your strength. It dwindles, slows far off among the repeating countries, hangs still for a heartbeat, and comes back, gathering speed, and lands in your palm, every time, no matter how hard you throw. The edge does not accept matter. and the universe itself returns your offering. Then you raise the lamp and send a flash outward, a pulse of pure light, and you count quietly in the dark. The flash crosses country after full-sized country, infinitely many of them, the journey no traveler could finish in eternity, and it reaches the rim of the world, the actual infinitely distant boundary, and it bounces. And before you have counted very far, the light comes home, a faint answering glint from the end of the universe, arriving on schedule, as if infinity were a courtyard wall. In anti-de Sitter space, you could spend an evening flashing greetings at the edge of everything and timing the replies. The boundary is infinitely far away, and it answers back. Physicists describe this by saying that AdS is like a box, a universe in a bottle whose glass is genuine infinity, and they mean it with unusual precision, because the mathematics shows something stronger and stranger still. That reflective wall has consequences physicists are still charting. In 2011, numerical relativists discovered that the box-like character makes pure AdS remarkably fragile. Sprinkle a small ripple of energy into it, and instead of dispersing harmlessly to infinity the way it would in flat space, the ripple reflects off the boundary, returns, crosses itself, reflects again, and with enough patience, the endlessly refocused energy can pile up and collapse into a black hole. An infinite universe, whose edge keeps handing your disturbances back to you, is, in a precise sense, claustrophobic. And in the 1990s, theorists exploring why gravity in our own world is so strangely feeble compared with the other forces built influential models in which our familiar universe is a thin slice suspended inside a 5-dimensional AdS bulk, with gravity leaking off the slice into the extra saddle-shaped dimension. Those Brownie world models are speculative, and they are not tonight's destination, but they mark the moment the physics community began taking seriously the thought that anti-de Sitter geometry might be more than a toy. The stronger statement is this: in anti-de Sitter space, you cannot even predict the future of the interior without first declaring what happens at the boundary. In flat space-time, if you know the complete state of the universe at one instant, everything everywhere at a single tick, the laws of physics determine all that follows. In AdS, that recipe fails, because light can reach the edge and return in finite time, which means fresh influence can arrive from the boundary before your prediction has gotten anywhere. The technical phrasing is that AdS is not globally hyperbolic, and the practical meaning is that the wall has a say. To do physics in the bulk at all, you must legislate boundary conditions, rules of conduct for the infinitely distant. Does light reflect there, and how, and what may pass? The edge of this infinite universe is not bookkeeping, it is part of the dynamics, a participant, load-bearing in the strictest sense there is. Notice also the fine structure of the connection. Every geodesic arc of the Poincaré disk, every one of those circle segments meeting the rim at right angles, hangs from 2 points on the boundary and dips through the interior, sometimes near the rim, sometimes through the very center of the world, and every event in the bulk lies on infinitely many such arcs. The boundary is not connected to the bulk at its edges only. It is stitched through the whole of it, every point of the wall, threaded by geodesics to every region of the interior, a weave, not a wrapper. Patterns declared on the surface propagate inward along the weave and shape the middle of the universe. Say the least you can say, and it is already enormous. The surface organizes the bulk. Say a little more, as a generation of physicists was about to, and you arrive at the idea that made this obscure saddle-shaped toy the center of theoretical physics for the last 30 years. Perhaps the surface does not merely organize the bulk. Perhaps the surface is the bulk. Part 11. The universe on the surface. Remember the clue that was glowing quietly in the back of your mind. When Hawking's calculation confirmed Bekenstein's heresy, physics was left holding a fact it could not digest. The information capacity of a black hole, the densest information storage nature permits, grows with the area of its surface, not the volume of its interior. Everywhere else in the world, capacity is volume. Libraries, hard drives, brains, all of them count their contents by the interior space available. Black holes count by the wrapping paper. Through the 1980s, this stayed a curiosity, an accounting oddity at the bottom of a gravity well. Then two theorists decided to take it with full, reckless seriousness. Gerard Hooft, the Dutch Nobel laureate, proposed in 1993 that the area law is not a quirk of black holes, but a confession from quantum gravity itself, that the physics inside any region of space, any region at all, can be completely described by information living on that region's boundary surface. Leonard Susskind gave the proposal its permanent name 2 years later, in a paper titled The World as a Hologram. The name was chosen carefully. A hologram, the kind on a credit card, is a flat object, a two-dimensional film, etched with an interference pattern, and yet it encodes a full three-dimensional image, every parallax, and every depth recoverable from a surface with no depth at all. The holographic principle proposed that the third dimension of our world might stand in exactly that relation to some distant surface. Not an illusion, but not fundamental either. Encoded. For 4 years, the principle hovered, grand and untestable, a slogan, in search of an equation. The equation arrived in November of 1997 from a 29-year-old Argentinian physicist at Harvard named Juan Maldacena, in a paper whose title mentions neither edges nor holograms, the large N-limit of superconformal field theories and supergravity. Beneath the armor of that title sits the most consequential physics paper of the past 3 decades, and its content can be said in one breath, now that you have spent tonight assembling every piece of it. Maldacena presented overwhelming evidence that a certain quantum field theory, a mathematical cousin of the theory that governs quarks and gluons, defined on a flat spacetime, is exactly equivalent to a full theory of quantum gravity, a string theory, living in an anti-de Sitter space of one higher dimension. And the flat spacetime where the quantum theory lives is not just any flat spacetime. It is the conformal boundary of that anti-de Sitter space. The theory on the wall of the cylinder is the theory of the interior. The relationship is called the AD-S-CFT correspondence. CFT for conformal field theory. And there is our word one final time, completing the journey it began as a property of Penrose's maps. The quantum theory on the boundary is conformal, indifferent to scale, caring only for angles, which is precisely what fits it to live on a boundary whose distances were surrendered in the compactification and whose angles were the thing preserved. Let me say carefully what equivalent means here, because it is the strongest word in a physicist's vocabulary. It does not mean the two theories resemble each other or approximate each other. It means they are the same theory written in two languages. Every object, every event, every process in the gravitational interior corresponds to some configuration of the quantum fields on the boundary, and every calculation performed in one description has a matching calculation in the other that yields the identical answer. A star orbiting in the bulk is, in the boundary language, a particular shimmering pattern in the quantum fields, evolving on the wall. A graviton in the interior, the quantum of gravity itself, is a certain collective ripple of boundary fields. A black hole, the object that started this entire investigation, translates into something wonderfully mundane, a hot soup of boundary particles in thermal equilibrium, its temperature none other than Hawking's, its troublesome entropy now simply the ordinary entropy of the soup, area law and all, explained at last, because what looked like a mysterious surface bookkeeping in the bulk is volume bookkeeping on the boundary, one dimension down, where it is no mystery at all. Depth into the bulk, distance in from the wall, corresponds on the boundary to scale, to the size of the patterns you examine, so that physics near the wall is fine-grained boundary physics, and physics in the far interior is the broad, coarse weather of the boundary fields. The direction you would call inward, pointing toward the heart of the universe, is, in the other language, nothing but zooming out. No general proof of the correspondence exists to this day. What exists instead is nearly 3 decades of attempted demolition, thousands upon thousands of independent checks, quantities computed both ways, in cases chosen specifically because a disagreement seemed likely, and the two languages have never once contradicted each other. Maldasena's paper became the most cited publication in the history of high-energy physics, its citation count in the tens of thousands, and within months of its appearance, Edward Witten, and independently the trio of Stephen Gubser, Igor Klebanov, and Alexander Polyakov, had supplied the working dictionary, the explicit rules for translating any question on one side into a question on the other. At the field's great annual conference in 1998, a hall full of the world's string theorists celebrated by dancing and singing a parody song called the Maldacena. It is difficult to overstate what the discovery did to the field's morale. Quantum gravity, the problem that had humiliated physics for 70 years, the problem of what space-time is made of, had been given, for one family of universes at least, a complete and exact answer. In an anti-de Sitter world, quantum gravity is ordinary quantum physics without gravity, on the boundary, in one fewer dimension. The hardest problem in physics dissolves into a solved one, at the edge of the universe, and the dictionary earns its keep on real matter in real laboratories. The correspondence is what physicists call a strong-weak duality, meaning that precisely when one side becomes hopelessly difficult, the other becomes easy. Some of the most impenetrable systems we can create, quantum matter, in which every particle interacts fiercely with every other, translate into clean, tractable gravity problems in a fictitious ADS bulk. When the collider at Brookhaven melted gold nuclei into a plasma of free quarks and gluons at trillions of degrees, the stuff turned out to flow like a nearly perfect liquid, with a viscosity so low that no conventional method could account for it, and the number was explained by translating the plasma into the physics of a black hole horizon in 5-dimensional ADS, a calculation from 2004 that predicted a universal lower bound on viscosity which the real plasma respects. Condensed matter theorists borrow the same dictionary for exotic superconductors. Nuclear physicists, atomic physicists, quantum information theorists, all of them now routinely consult the geometry of a universe that does not exist to compute the behavior of matter that does. Holography, whatever its ultimate metaphysical standing, computes. Then, in 2006, the correspondence gave up its most closely held secret so far. Shinsei Ryu and Tadashi Takayanagi asked a boundary question: how much quantum entanglement links one region of the wall's fields to the rest, and found that the answer is computed, in the bulk language, by geometry alone. The entanglement between boundary regions equals the area of a certain minimal surface draped through the interior, a soap film of space-time hanging from the boundary of the region in question. Entanglement on the edge is distance and connection in the bulk. Follow that thread, as Mark van Ramsdonk and others did, and you reach a conclusion that would have sounded like mysticism in any earlier century. Dial the entanglement between two halves of the boundary down towards zero, and the bulk between them stretches, thins, and tears, space itself pulling apart into disconnected pieces as the quantum correlations that stitched it together are removed. Space-time, in this picture, is not a stage. It is a fabric woven from entanglement, thread by quantum thread, and the loom sits on the boundary. The interior of the universe, with all its distances and depths and interiors, is the derived thing, the image, and the flat quantum world at infinity is the original. The weave keeps revealing new stitches. In 2013, Maldacena and Susskind proposed that any two entangled particles, even a humble laboratory pair, are joined by a microscopic bridge of space-time, a wormhole too small and too twisted to traverse, so that quantum correlation and spatial connection are one phenomenon seen at two scales. And when theorists asked how the boundary manages to store the bulk so robustly, with the innermost interior recoverable even if you lose access to patches of the wall, the mathematics that answered was quantum error correction, the same discipline that protects the fragile memories of quantum computers. In this reading, the interior of the universe is encoded on the boundary, redundantly, the way a well-designed code smears one bit across many, and space-time itself has the architecture of a self-repairing memory. These ideas even circled back to slay the oldest dragon in the den. Within the last several years, holographic methods produced the first calculations showing in detail how information escapes an evaporating black hole, addressing the paradox Hawking's boundary calculation created half a century ago, and they did it by taking the boundary description as the truth and following it wherever it led. Now bring back the proverb we planted in the middle of the night. The map is not the territory, except here, at the edge of an infinite universe. The mathematics has been trying to tell us, for nearly 30 years, that the humble slogan finally fails. The boundary description is not a chart of the bulk. It is exact, complete, and by the lights of many physicists, more fundamental. The map, at last, may be the territory, which leaves only the question you have been patient with all night. What about our universe? What about your edge? Part 12. What the edge of an infinite universe would look like. Honesty has to come first, before the answer, because this channel owes you the truth, even at the hour of the night, when a comforting story would be easier. We do not live in anti-de Sitter space. The magnificent machinery of the last hour, the cylinder, the answering wall, the exact dictionary, all of it was built for a universe with a negative cosmological constant, a vacuum that pulls inward, a cosmos with the temperament of a closed bell. Our universe is the opposite case. Our vacuum pushes outward. Dark energy is accelerating our expansion, and a universe like ours, run forward, becomes ever more like de Sitter space, the exponentially inflating solution Einstein disliked, the first of our three shapes. And for a de Sitter universe, the honest Penrose diagram delivers a quiet shock, the one I asked you to file away hours ago. The boundary of our space-time, drawn honestly, does not stand at the end of space. In an accelerating universe, the compactified map closes not with a wall at infinite distance, but with a surface at infinite future, a boundary that lies at the end of time. If our universe has an edge in the rigorous sense we have spent tonight constructing, it is not somewhere you could point a telescope. It is somewhen. It is the infinitely far future, the final surface on which all our world lines end, and every moment of your life is aimed at it. No one has yet built the dictionary for that edge. This is the frontier, and it is genuinely open. In 2001, Andrew Strominger proposed a de Sitter version of the correspondence, a DSCFT, with the dual theory living on that boundary at the end of time, and in the years since, some of the most formidable people in the field have circled the problem, including Susskind, who frames it with a thought experiment he calls the census taker, an observer at the far end of eternity, looking back, in principle, at everything that ever happened. The de Sitter case fights back in ways the Saddle universe never did. Our horizon, unlike the ADS wall, is personal, each observer wrapped in their own, and the finite information budget it implies, that 10 to the power of 122 bits we have discussed on this channel before, as the information capacity of our cosmos, sits uneasily with the infinities the mathematics wants. There are partial results, tantalizing patterns, published attempts to test holographic pictures of the early universe against the sky's oldest light. There is no verdict. The construction that would settle what our own edge is has not been completed by anyone, and it may be the largest single prize in theoretical physics. I told you at the start of tonight that the boundary of an infinite universe may be as real as the universe it contains, or more real. For the Saddle universe, The mathematics says exactly that. For ours, the mathematics says, so far, not yet, ask again in a generation. That is not a failure of the story. That is what it feels like to be alive while the story is still being written. Before the answer, one more piece of housekeeping, because this subject attracts myths the way a lamp attracts moths, and you deserve to know where the science actually stands. You may have seen headlines announcing that physicists discovered we live in a simulation. The holographic principle says nothing of the kind. A duality between two physical descriptions contains no computer, no programmer, and no intent. And the simulation notion is a separate philosophical argument that merely borrowed holography's press coverage. You may also have seen claims that experiments found the first evidence we live in, a hologram. Two real projects sit behind those stories, and their real results are instructive. At Fermilab, a physicist named Craig Hogan built an instrument called the holometer to listen for a conjectured holographic jitter in space itself, a pixelation of reality his particular model predicted. And in 2015, the instrument reported, cleanly, silence. No jitter, at the finest sensitivity ever achieved. That null result retired Hogan's specific model and left the mainstream holographic principle untouched, because the mainstream principle never predicted such noise in the first place. And in 2017, cosmologists tested a class of holographic models of the early universe against the sky's oldest light, and found them statistically competitive with standard inflation for part of the data, a legitimate, published, modest test, reported in some places as proof we are a projection. It was no such thing. The honest scoreboard reads like this. Holography is mathematically overwhelming in the saddle universe, physically productive in the laboratory, and, for our own cosmos, unproven, unfalsified, and under construction. The fringe versions promise a projector hidden behind the world. The real mathematics proposes something stranger. No projector, a screen that is self-sufficient, and a world that may be its reading. So now, at last, the question itself. What would the edge of an infinite universe look like? You have earned the answer, and the answer has layers, like everything tonight. If you mean, what would you see if you traveled outward forever? The answer is nothing, and now you know why nothing. You would pass fence after fence, horizon after horizon, each one real, and none of them an end, tiles of full-sized country forever, and the edge would stand off at its fixed infinity, like the rim of Escher's disk, visible to mathematics, untouchable by you, because you are made of matter, and matter never reaches the edge of the universe. Only light can touch it, and even light tells no tales, except in a saddle-shaped world, where the wall hands the light back. That was the rule we learned on the diamond, and here at the end, it becomes something gentler than a prohibition. It is a division of labor. You were never built to arrive at the boundary. You were built to be, if the holographic reading of our best mathematics is right, among the things the boundary keeps. Because that is the final layer, the one the whole night was for. In the most fundamental description physics currently possesses, the edge of an infinite universe looks like the universe. Not a wall around everything, but a rendering of everything, the entire interior written, exactly and completely, one dimension down, on a surface that distance cannot reach. Every galaxy in the bulk is a pattern on it. Every black hole is a warm stirring of its fields. Every quiet room with a voice talking late into the dark, every listener, every drifting thought you have had tonight, would correspond, precisely, to some configuration at the boundary, not as a copy or a shadow, but as the original text, of which the world you touch may be the translation. The picket fence we built in the first hour, the little boundary that made our patch feel like home while the plane ignored it, has come all the way around. Physics went looking for the fence at the end of everything, and found, in its most radical mathematics, that the fence may be the foundation, that the enclosure may be doing the enclosing in both directions, holding not just the shape of the universe, but its substance. The map is not the territory, we said, and we watched the proverb strain all night, and at the edge of an infinite universe it finally lets go. There, the map and the territory are one document. And if that is true of our universe, then the childhood question, the one you were told was broken, has an answer no adult ever offered you. What is at the edge of everything? You are. Everyone is. Everything is. Held at the one address in existence that nothing can leave and nothing needs to. It matters, too, that thoughtful physicists read even that last sentence 3 different ways, and the disagreement is worth hearing as you settle. Some hold the sober view that boundaries at infinity are magnificent bookkeeping, tools that compute and nothing more, and that asking what the edge is really like mistakes the scaffolding for the cathedral. Others hold the symmetric view that bulk and boundary are 2 complete tellings of one reality, neither more true, the way a song is neither the score nor the sound wave, but the thing both capture. And a growing school holds the radical view that the boundary theory is the fundamental one, that interiors, distances, and depth are emergent conveniences, in which case the edge is not the least real part of an infinite universe, but the only strictly real part of it. Nothing in tonight's story forces the third reading on you, but it is the one the last 30 years of results keep leaning toward, and falling asleep while holding a question all of physics is still holding is not a bad way to end an evening. Hold that picture as the night winds down, and let me leave the last stone unturned, on purpose, because it deserves its own evening. Between the boundary and the bulk runs that exact dictionary, the correspondence itself, the machinery by which a flat quantum world without gravity composes an interior with black holes and falling stones and time. How the translation actually works, entry by entry, entanglement into distance, information into geometry, is one of the great detective stories in modern science, and it is still short its final chapter, and some other night we will read it together. For now, it is enough to know what you know. The universe may be infinite. You may be one of its endless residents, unrepeatable all the same, and infinitely far from here, in a direction that is not a direction. There may be a surface that has missed nothing, where the whole story, including this small hour of it, including a tired mind finally letting go of a question it has carried since childhood, is already written down, and kept, and safe. What would the edge of an infinite universe look like? It would look like everything. It would look like tonight. Sleep well inside the pattern.